My name is Mebin Joseph. I am a PhD student working with Professor R. Balasubramanian and Dr. Gautam Shekhar. My co-author, Professor Balasubramanian, was supposed to attend the conference and present the paper, but due to some personal emergencies, he couldn't travel. Therefore, I will be presenting the paper, I will be giving the talk today. Hi all. I will be presenting the distinguishing attacks that we have built on ultra lightweight WG ciphers. This work was jointly done with Dr. Gautam Shekhar and Professor R. Balasubramanian. This is the outline of my presentation. We know that with the advent of these kind of hardware constrained devices, the importance of lightweight cryptography is currently growing. LFSR based constructions are very popular among lightweight stream cipher designs, and to augment the linear complexity of the LFSR, we'll be using a nonlinear function, and these kind of combinations are called nonlinear filter generators. WG family of stream ciphers are very good examples of nonlinear filter generators, and in the nonlinear function used in a WG family of stream cipher is an n-bit to 1-bit transformation, and that is defined over the Galois field 2 power n. Based on the value of n, there are 5 different members of the WG family, and namely WG29, WG16, WG8, WG7 and WG5. WG29 was the first member of this family, and it was a well received entrant to the eCrypt eStream competition. WGA and WGB are patented variants of WG8 and WG16. We have given this name to distinguish them from the non-patented and patented variants. And WGA and B are covered by a US patent, and the patent number is given here. WGA, it forms a subfamily under the family WG, and here it is made up of 3 ultra lightweight ciphers, and WGB family is made of 31 lightweight ciphers, and WGA is proposed to be used in an RFID system for anti-counterfeiting. WGB is proposed for securing 4G networks. The secure RFID system where WGA is used has been exhibited in a conference conducted in United States in 2015. This is a web page displaying those details, and the WGB will be used for securing 4G networks, and those details are given in this web page. This is a web page of University of Waterloo, Waterloo Commercialization Office. So I will be detailing the specifications. WGA is made up of, means it is using a key of size 80 bits and an initialization vector of size 80 bits. LFSR is defined over the field f2 power 8. This is a primitive polynomial of the field, and the feedback polynomial of the LFSR is given here. This is the schematic diagram of WGA. It consists, the LFSR is made up of 20 stages, and omega power 38 is the multiplication factor used. This is the multiplication operand used in the field f2 power 8. This is an exponentiation function, and this is a permutation function, and TA is a trace function. So permutation function and trace function jointly forms the transformation. So these are the equations for permutation and trace functions. The exponentiation function computes SA19 power d, where d is the decimation factor. So the decimation factor can have 3 optimal choices, 30, 19 and 61. So based on that, there are 3 ciphers in this WGA family. The cipher corresponding to the decimation factor d will be denoted by WGA subscript d. These are the initialization and keystream generation algorithms of WGA. So in the initialization phase, the key and IV are loaded into the LFSR, and the LFSR will be updated for 40 cycles. During the keystream generation phase, at each cycle 1 keystream bit ZAI will be generated. This will be the output of the transformation, and the LFSR will be updated using this recursion formula. WGB is having a similar structure similar to that of WGA. and it consists of a 32 stage LFSR, and in WG B it uses a key of size 128 bits and initialization vector of size 128 bits. Remaining components are almost similar. These are the transformation function, permutation function, trace functions used in WGB family. Exponentiation computes SB31 power D. There are 31 optimal choices of D in case of WGB, and the cipher corresponding to the decimation factor D will be denoted by WGB subscript D. Now we will be going on to the motivational observations. So we detected input-output correlations in the WG transformations used in WGA and WGB. This has been computed through exhaustive search over the entire input space of WG transformation. So the input spaces were of sizes 2 power 8 and 2 power 16. We have detected two types of input-output correlations. In one case, output bit was correlated to a single input bit. In another case, output bit was correlated to an XOR sum of the input bits. So these two tables gives the correlation probabilities for WGA subscript 61. Here, the probability that ith bit of input equal to the output of transformation is given, and here the ith bit of the product of input and omega power 38. This is the multiplication factor used. The ith bit of that equal to the output of the transformation, that probability is given. Similarly, we have computed the probabilities for WGB 157. Again, for WGA 61, we find that in this particular table, the bias will be maximized when I equal to 5. So 2 power minus 4 is the maximum bias. So therefore, hereafter we will be considering the case I equal to 5. Now, so when I equal to 5, we can say that the fifth bit of the product of input and omega power 38 will be equal to the output of transformation. So this is the key stream generator used in WGA 61. Let us assume that SA0 is the 20th stage of the LFSR at t equal to 0. And now the output, the key stream will be, bit will be ZA subscript 0. So from this equation, we will find that the key stream bit is biased towards SA0 into omega power 38. This is a multiplication factor, and the fifth means it will be biased towards the fifth bit of this value. Similarly, we also know that from the correlation probability, the fifth bit of the input is biased towards the output of transformation function. Therefore, at t equal to 9, 20th stage of the LFSR will be having SA9 as the content, and the fifth bit of this value will be biased towards the key stream is generated ZA9. Similar thing can be done at t equal to 11, t equal to 20, and we know that from the LFSR recursion formula, means it is given by SA20 equal to SA11 XOR SA9 XOR SA means the product of omega power 38 and SA0. Now since this is a linear relation, we can say that the fifth bit of SA20 is equal to the fifth bit of SA11 XOR the fifth bit of SA9 and XOR the fifth bit of the product. Now we know that this particular value SA20 subscript 5, this is biased towards ZA20. Similarly, SA11 subscript 5 is biased towards ZA11. Similarly, all these bits of the LFSR are biased towards some of the key stream bits. Therefore, we can substitute these key stream bits for the bits of the LFSR, and we will get ZA20 XOR ZA11 XOR ZA9 XOR ZA0 equal to 0. This is not exactly equal to 0, but with a probability it is equal to 0. We can generalize it as ZA t plus 20 XOR ZA t plus 11 XOR ZA t plus 9 XOR ZA t equal to 0, where t is greater than 0. This can be, this will be satisfied for any WGA subscript D, for any family of, any member of the WGA family. Similarly, for WGB family, we will be able to compute such a linear combination of the key stream bits. Now we need to compute with what probability this particular combination is, linear combination is satisfied. Now let us assume that Z cap A, that we will be calling as a sample. Let sample equal to the linear sum of the set of key stream bits that we have already mentioned, and let Pi equal to the probability that ith bit is equal to the output of the transformation, and Qi let it be equal to the ith bit of, means the ith bit of product equal to the output of the transformation, that probability. Then by Matsui's piling up lemma, we will be able to compute the probability that ZA cap equal to 0. That means what is the probability that sample is equal to 0. So that is given by this equation. Similarly, we can compute the same for WGB. Now, from the correlation probability tables that we have mentioned earlier, P5 and Q5 we know they are equal to 0.5 minus 2 power minus 4 and 0.5 minus 2 power minus 6. So based on that, we can compute the probability Z cap A equal to 0 equal to 0.5 plus 2 power minus 15. Now the question arises, can we obtain a better estimate of the probability? Because many of the input bits are correlated towards the output bit. So is there any possibility to obtain a better estimate? Answer is yes, by combining input bits. So what we have done is, we have chosen a set of input bits, and the combination of that, what is the probability that the linear sum of those input bits equal to the output of transformation, that we have computed. And for S1 equal to 0, 3, 5, 6, this is the set of input bits. So when 0, 3rd, 5th and 6th input bits are XORed, and the probability that it is equal to the output of transformation we have computed. Similarly, 0th, 3rd, 5th and 6th bits of the product of this particular value are XORed, and what is the probability that it is equal to the output of transformation we have computed. And those two probabilities, when we use it to compute the final probability, we get the value 0.5 minus 2 power minus 12.49. We can find that it will be, here we got the bias as 2 power minus 15, and here it has been improved to 2 power minus 12.49. So this is the best bias that can be obtained using this method. Similarly, we computed for WGB 157, and the bias we have obtained is 2 power minus 25.49. So these are the probabilities that the sample equal to 0 for each case of WGAD and WGBD ciphers. Now we will be computing the attack complexities. Now the attacker is having, he knows that there is with some probability with some bias, the sample or the linear sum of the key stream bits is equal to 0. Now based on that, he wants to compute how many samples are required. Now let n equal to the number of samples available to the attacker. ZA is the sample, and D equal to the distribution of the sum of the samples, and D dash will be the distribution of Z given that WGA 61 is an ideal cipher. When it is an ideal cipher, this sample will be behaving in a random phase, like the probability of sample equal to 0 will be 0.5, and P is the probability that sample equal to 0, that we have calculated, and P dash will be the probability that when it belongs to the distribution D dash, that is the sample is from an ideal cipher. In that case, it will be 0.5. Mu and mu dash are the means, and sigma dash are the standard deviations of D and D dash. Now when this condition is satisfied, that is absolute value of mu dash minus mu greater than 3.62 into sigma dash plus sigma, when this is satisfied, we can say we will be able to distinguish WGA61 from random with a success rate of 99.99% and false positive rate of, there will be a false positive rate of 0.01% too. And if we substitute for mu dash, mu, sigma dash and sigma, then we will be getting that n should be, the number of samples should be greater than 3.62 square divided by p minus 0.5 whole square. For WGA61, we know that the p value is equal to 0.5 minus 2 power minus 12.49. So based on that, we will be able to compute n must be greater than 2 power 28.69. Similarly, we can compute for WGB 157. And for the other members of the family, we have computed complexities, and we can see that all the entire WGA and WGB family can be attacked based on this using our method, and these are the complexity requirements for our attack. The highlighted ones are the maximum complexity requirement in each family. We can find that WGA requires practical complexities. Therefore, we have experimentally verified our attack on WGA. What we have done was we have chosen 2 power 20 key IV pairs at random. Then each key IV pair was given as input to the WGA cipher, and 1000 key stream bits were generated. And from the 1000 key stream bits, 970 samples can be generated. And totally from 2 power 20 key IV pairs, we will be able to generate approximately 2 power 30 samples. And from 2 power 30 samples, we can compute what is the probability that sample is equal to 0. And we repeated this experiment some 10,000 times, and the mean value of the probability that sample equal to 0 was computed. And these tables give here, this is the theoretically computed probability that sample is equal to 0. This is the experimentally computed probability that sample is equal to 0. And we can see that in case of WGA13 and WGA61, they agree very closely. But in case of WGA19, there is a slight variation, and the reason for that is currently under investigation. So I have presented the attacks on WGA and WGB ciphers. The data requirement for a success rate of 99.99% is at the most 2 power 29.07 samples in case of WGA, and in case of WGB it is 2 power 56.84 samples. Accordingly, we can compute the time requirement also. These are the first attacks on WGA and WGB. These attacks are due to the low nonlinearity and low correlation immunity of the WGE transformation used in these ciphers. So the measures to improve the security of these ciphers are, one method is to increase the number of tap positions of the LFSRs. So by increasing the number of tap positions, we will be able to increase the complexity of the attack, and the attacker won't be able to mount a practical attack. Then another method is using a different LFSR multiplication factor, that is which is equivalent to omega power 38 in WGA. If we use a different multiplication factor, we have to take care that the linear complexity of the LFSR is not affected. Along with that, we must be able to take care that the attacker should not be able to identify a linear approximation that can result in our attack. Then the best method that we prefer is that we suggest to use a filter function that is having a good correlation immunity, because if we are following the other two methods, the inherent weakness of the WG transformation still exists, and the attacker may be able to come up with some new attacks exploiting that particular weakness. But if we are using a filter function having good correlation immunity, then that may not be possible. So that's all. Thank you. And if you have any questions, you can address it to my email ID, mebinjp@gmail.com.